Assalamu alaikum. Knowledge Graph Deep Learning, a case study in question answering in aviation safety domain. Project research paper by Ankush Agarwal, Rajgiti, Shreya Latha. That was published in the proceedings of the 13 language resources and evaluation conferences in 2022. I am Mahir Amin and I will brief you about the followed case studies published in June 2022. So here's a highlight of our paper: Introduction, Related Work, Data Repositories, Aviation Knowledge Graph, the Question Answering System, Experimental Setup, Result and Analysis, Conclusion and Future Work with references. So first, let's familiarize ourselves with the terminologies commonly employed within the research paper. Knowledge graph. What is knowledge graph? Knowledge graph is a way of organizing and representing the data that captures relationships and connections between entities. Here, as you can see in the example given below, the circles represent the nodes. The nodes are actually the entities. Entities can be anything, a person, or anything like chair, tree, or date, and edges represent the relationship between these entities. Here's an example of knowledge graph. As you can see, the entities in nodes: a programmer is an entity, Andy is also an entity, 1983, ME 50K, Washington. Every single entity, every single node that is represented as a circle is entity, and the arrows are representing the relationship. For example, Andy, the arrow between Andy and Washington is directed towards Washington, and the relationship is defined as born in. That means Andy born in Washington. Similarly, Washington, that relationship between Washington and 50K is population. That is, Washington has 50K population. So knowledge graph in deep learning has actually three main tasks. That is how we construct knowledge graph and then extract knowledge from it, information from it. So first we use different techniques: entity extraction, relation extraction, ontology mapping, entity mapping, etc. to construct a knowledge graph, and then we add the knowledge of knowledge graph to the machine learning techniques that classify and find similarity, then predict the answer. So first, let's zoom in on the classification task. First, the input space where the knowledge graph lives, and then when any machine learning technique will be applied on the graph, it will give us a output space where we can make a classification. So we will actually train the model such that it transforms the graph and predicts a number between 0 and 1 for every node. If it predicts the number between 0 and 0.5, it means that it belongs to category 1, and if it results in 0.5 to 1, that means that that any input value or entity belongs to the category 2. So what is actually question answering system? Question answering models are machine or deep learning models that can answer questions given some context and sometimes without any context. So they can extract answer phrases from paragraphs, paraphrase the answer generatively, or choose one option out of a list of a given options, and so on. Aviation knowledge graph. What is aviation? Aviation is a study related to the aircrafts or the system operation of aircrafts. So the aviation knowledge graph will depend on it is constructed from accident reports, accidents cost, accident effects, aircraft, and aircraft information like who is the pilot of that aircraft and its meteorological conditions. But knowledge graphs are not as expressive as natural language sentences to explain complex events. So here is the challenge for us. So this motivates us the need for deep learning models such as BERT from Google and GPT-3 from OpenAI. Bidirectional encoded representations from transformers was introduced by Google in 2018 that contain 110 million parameters, and its encoder reads the text input and decoder predicts the output. GPT-3 Generative Pre-trained Transformer 3 was introduced by OpenAI in June 2020 and it contained 175 billion parameters. So the major contributions in this papers are aviation knowledge graph and question answering system that will be using two kind of deep learning techniques. Knowledge graph based question answering system uses a pipeline that converts natural language queries that a human asks into the SparkQL queries first and then fetch responding from the aviation knowledge graph. SparkQL is the standard query language and protocol for linked open data, and RDF. RDF is Resource Description Framework databases, and this is represented in the form of is a framework in which data is represented in the form of entities and relationships, as we have discussed earlier in the knowledge graph. So, how is it works? How does a query generate? Is it here we have select question mark subject, question mark predict, and object. So it contains triples, and triple consists of its words say the name says itself. Triple consists of three things, that is subject, predicate, and object. The subject is the main thing, that is whom or what is it talking about, and predicate is the action performed on any object, and object is the noun on which the action is performed. So here the query asks where subject, predicate, object, and it retrieves the all subjects, predicates, and object. Related work of this paper is the first one was in 2018 when the development of a knowledge graph construction system in the aviation risk field actually started. And then in 2019, Chang et al. Built an ontology for civil aviation security by extracting knowledge from the data sources in the form of entities and relations. But no prior work was done on the widely available NTSB accident reports. So the paper we are seeing now is the first attempt to combine knowledge graph and deep learning in the aviation domain for the question answering to the best of its knowledge. Data repositories accident. First of all is accident reports. Accident reports capture all the aspects of an accident and the aircraft name and the aircraft specification, pilot's name, its all details, environmental state, and a comprehensive description of a suspected cause of the accident. We will be going to look at an example as well of accident reports. Accident reports contain NTSB reports, National Transportation Safety Board reports, that is the investigation reports of civil US aviation safety reporting system ASRS reports. These reports gather information from pilots and crew members about close call events during flight journeys and what notification did they get. And airworthiness directives ADs contains notifications to owners of certified aircrafts about the unsafe conditions that exist in particular aircraft models, like if the pilot and the crew was timely informed about the any hierarchy of factual descriptors like time, place, aircraft models, engine component manufacturer, etc., and analytical descriptors of the occurrence of accident like how the accident occurred and what was the type of event that occurred at time and its explanatory factors as well. So this is how an NTSB report looks like. First of all, we are given the detail of what was the location where the accident occurred, its date and time, what was the aircraft, and what was the event, accident number, registration, aircraft damage, injuries, etc. Then the whole full analysis of the accident is given in the report, its probable cause and findings. Adaptive taxonomy looks like this, where it works in the form of hierarchy. Like aircraft handling related event is the main category, and then in that category, aircraft altitude related event are mentioned, and then altitude related event are then further divided into altitude burst. Altitude burst is when the specified altitude isn't maintained and flying too close to the ground or other altitude related event, etc. Aviation knowledge graph is constructed using NTSB reports and adaptive taxonomy. Pre-processing was done on NTSB reports. First, these reports were converted into text files, and different pre-processing techniques were performed, like stopper removal, PO stacking, lemmatization. In lemmatization, the root word of any word is found, like if we consider the word changer, changing, and changes, so its root word is lemmatization. In ontology creation, the root to leaf path is created using two techniques, that is mapping based on distance between word embedding and mapping based on keyword matching. Here is the sample of root to leaf path in adaptive taxonomy. The aircraft event is the main category, and then operation that contained operation of the aircraft related events and aircraft handling related event. And if you want to go to the cause of an event that occurred, then it goes to drag wing, rotor, port, float. In mapping based on distance between bird embedding, the embeddings are calculated for each path, and their distance between these embeddings is calculated, and the embedding with the node with the least distance is mapped to NTSB event, and its corresponding route to leaf path is also associated with NTSB event. Then mapping based on keyword matching. In this, we first tokenize the NTSB report events, then map each token to the nodes in the adaptive taxonomy, and then the node with higher similarity score is associated with NTSB event. Different extraction techniques include named entity recognition, that detects the entities from the text and then classify these entities into different categories. Term frequency. The example of named entity recognition is, here is the input text is given in the form of sentence, and the output is, it tells us that which word belongs to which category, like April 1, 1976 belongs to the category of date, and Cupertino, California belongs to the category of location. The term frequency term tells us that how many times a specific word appears in the document. And IDF tells us how rare a word is in the document. That is, term frequency is calculated by term frequency inverse document frequency is calculated by multiplying these both. An example is, consider a word that is T appears 20 times in a document that contains 100 words. So the term frequency would be calculated by the number of times a specific word appears in the document by the total number of words in a document. And then assume that a collection of related documents contains 10,000 documents, and the 100 documents can have the word T in it. So the IDF would be calculated by the log of the total number of documents by the number of documents that contain the word T. Then the final TF IDF would be calculated by multiplying both TF and IDF together. The C-value extraction technique helps in identifying terms that are also frequent but unique as well. It involves pre-processing, term extraction, term frequency, term discriminativity, C-value calculation, sorting and selection. How the knowledge graph is constructed. The pre-processed data of NTSB accident reports is input in the different entity extraction techniques and relation extraction techniques. And then on the other side, adaptive taxonomy that contained the knowledge of aviation category, events, and damaged aircraft that contains the accident number, airport, manufacturer's model, etc., and holding their all description is input to the construction of aviation ontology. Then the knowledge graph is constructed at the end in the form of triplets, that is subject, relation, and object. For example, the number of accident number, like its identity and its cause, and the object is shown in the form of triplet. Extraction technique includes sentence clustering, syntactic analysis, and DL-based techniques. The syntactic analysis is used where the corpus is annotated with part of speech tags to find hyponyms, and meronyms. Hyponyms give us a very broader view of a word like scratches. It generally belongs to category damage, but in hyponyms it belongs to the category marks, blemishes to a lower extent. And then in metonyms it would tell the elements of a specific word. Like for engine, it tells the word pistons, cylinders, spark plugs. So the instance was scratches are found on engine's nacelle. So we observed that nacelle is a part of engine. Nacelle. During the engine inspection, it was observed that the wing-mounted engine was working, but the fin-mounted engine was not working. How do we observe what is fin-mounted? So we observed from hypernyms, hoponyms, and metonyms, and the final observation was wing-mounted engine and fin-mounted engine are the types of engine. Knowledge graph construction is based on triplet that contains subject, relation, object, as I have told earlier. So what does it tell us? These triplets can be used in knowledge graphs or question answering system to retrieve relevant information and reason about the data in a structured manner. Now, in knowledge graph evaluation, 120 SparkQL queries with gold answer of different categories were tested, and the knowledge graph answered 83 questions right and attained the accuracy of 69.2%. The researchers had different challenges in construction of aviation knowledge graph. That was scalability, manual processing for creating ontology. Patterns may change with new reports. Like this research was based on 2022, and till now there could be a lot of events that aren't listed in this data set of this research. And also the domain specific terms in NTSB reports are not identified effectively by the extraction models. The question answering model, knowledge graph based question answering model utilizes aviation knowledge graph, and deep learning based question answering model utilizes the text that is in NTSB accident reports. The knowledge graph based question answering model outputs the answers directly, while deep learning based question answering model outputs the answer in the form of passage plus answers. Here's an example. Which accident occurred due to crosswind? The knowledge graph based question answering module will just list out the accident numbers against this question, while the deep learning based question answering module will not only list the number of accident but also list the passage about that accident. What helps us this? These passages help the user when answers fetched by the question answer system are incorrect. NL2 SparkQL pipeline. The question is asked in natural language query, and then the question type is classified. Then entity relation extraction is done on the dataset. Then triplets are generated and they are ranked accordingly. Then query is constructed and we get the final answer by the aviation knowledge graph. The question type classification classify the question into list, boolean, count, and then the keywords are identified from listing ask count to use in the select clause, and it then construct the where clause in the SparkQL query. For extracting entities, it is POS tagging, tokenization, n-gram tiling, and then it computes the similarity scores between the bird embeddings and map those retrieved entities in relation to the corresponding knowledge graph. SparkQL queries generated using the keyword specifying question type, listing for list, ask for boolean, and count for count. Models are based on retriever-reader pipeline. The retriever projects the question and all the passages in the collection to semantic vector space, and then the reader extracts and generates answer from the relevant passage. As in this flowchart, the question is asked, retriever projects the relevant passage to the reader, and then reader extracts the answer plus passage to the output. Data pre-processing involved, as I have also told earlier. PDF reports were converted to text, and then text contained passages that formed JSON files objects. JSON objects contain passage heading, passage text, and report ID. And then these JSON files were used by the BERT question answering model. Here are different models used. The test dataset contained 50 NTSB reports of 2002, and here is an example of question answer test set. Question was asked which accident are caused due to pilot's failure to maintain control leading to collision. The answer was in the form of list of 2 accidents, and then the passage related to each accident was also mentioned. The result we got from the case study is, here are different models, and then in the last combination of two models. And what is exact match? Exact match is if the predicted answer matches exactly, if the first predicted answer matches exactly the actual answer. And similarly semantic accuracy, but it doesn't rank the answer. Exact recall match the actual answer to the predicted answer. Similar is the case for semantic recall. For BM25 BERT, the exact match was 0.013, and knowledge graph question answer was 0.347, BERT question answer was 0.040, GPT-3 was 0.600, and combination of knowledge graph question answer plus BERT question answer it was 0.349. Combination of knowledge graph question answer plus GPT-3 question answer it was 0.5500. As you can also see, 0.600 for GPT-3 question answer worked the best for exact match, while for exact recall, semantic accuracy, semantic recalls, and passages, semantic accuracy and semantic recall, the combination of knowledge graph question answer plus GPT-3 question answer model worked the best. So this module achieves 29.3% accuracy and 9.3 increase in accuracy over knowledge graph question answer and GPT-3 question answer system individually, respectively. The researcher had few limitations, like knowledge graph question answer can answer questions efficiently only when valid spark queries can be formed. The BERT question answer system suffers from the lack of fine-tuning. Conclusion in future work is this, that knowledge graph in this paper was constructed on only NTSB reports. In future, it can be constructed using ASRS reports and ADs, etc. Thank you.